So good morning, everyone, and thank you for attending this lecture. Today we are going to discuss about edge computing for Earth observation. We are talking about challenges, what is edge computing, why we are doing it, and why we want to apply AI on board satellites. Just a very brief introduction about me. I'm Innovation Officer in the ESA PhilAb and Advanced Concept Study Office. I'm based in Esrin in Italy. I'm also technical committee co-chair of the IEEE GRSS Science Informatics, and the topic of interest are indeed edge computing for space, artificial intelligence, and disruptive computing paradigms. So at the end of this lecture, I hope you will be able to describe the concept of edge computing and its main application for Earth observation, describe the main hardware devices for edge computing in space, the main challenges, and more or less the current research trends. So today we are going to talk indeed about edge computing and why it's applied in space, what is edge computing in general, the application of AI in space, so the edge computing. We are going to discuss a bit about the hardware because it's a fundamental element, technical challenges and current trends. And then we will try to give a bit more the conclusion of what's the state of the art. So to understand what edge computing is, it's very useful to start from what cloud computing is. As you know, cloud means processing the data in the cloud, over the internet, basically. So you will have a lot of sensors that can be whatever, your computer, your mobile phone, cars, or any kind of domestic appliance providing data over internet and data processed and distributed everywhere, basically. Of course, despite this paradigm works very well, one of its main limitations is that it's producing a lot of raw data over internet or in general over the cloud itself. So one of the approach to solve this issue is to process the data, as we say, close to the device itself, at the edge of the network. That's why we are talking about edge computing. So edge computing means provide the system, so the sensor itself, of computing capabilities to reduce the data that you're going to inject into the network itself. So you might wonder why we are talking about this when we discuss about Earth observation. To understand that, we need to discuss how Earth observation mission work nowadays. So nowadays, the most operational paradigm is what is called bent pipe. What is the bent pipe? So here you have an old schematic of the Sentinel-2 missions. As you can see, the satellite are the dot whites that you can see. And the satellite acquire the data over the orbit, and then they can transmit. That's not exactly true, but just for sake of understanding, the data only when they are close to the red dots that are the ground station. It's called bent pipe because when the satellite passes over the ground station, it receives a command from Earth, and then you reply with the data, creating a bent pipe. So do you see any limitation on this paradigm? Of course, the paradigm works in the sense that it's basically how the whole Earth observation mission, including the scientific mission, work nowadays. So the paradigm works very well when you want to collect a lot of data and you want to store all of it on the Earth. But of course, if we come back to the slide, you can see that if you acquire the data just after the pass of the ground station, the next time you can send it when you find another ground station again. So in the worst period, in the worst case, it might be 100 minutes afterwards, hours afterwards. And so the paradigm overall is not very good to transmit only the information that you need to Earth very quickly. It's good when you want to provide a lot of data. Of course, our satellite are the sensors, and the ground, when you're actually processing all the data and storing all the data, is our cloud. So what it could be one solution to solve this problem? Well, if you see this comparison what I showed you before, it becomes quite easy to think about moving computational power on board the satellite itself to pre-filter the data. And in particular, using artificial intelligence, since it's basically nowadays one of the state-of-the-art algorithms to process Earth observation data. So the paradigm that you see is going to become a bit more complex. The satellite that you see here is basically one satellite. Let's assume the satellite passed over an area with a fire. The satellite itself can process the data directly on board. And as soon as you do it, you can create a sort of heat map or fire map. And you know immediately there is something that you want to alert, to send an alert to Earth very quickly. Of course, the satellite needs to have a way to do it. So you need a way to communicate with other satellites and send actionable information. Nowadays, there are satellites that act as a relay node. So you can send them the information and they send them to the ground. If you do that, you can close the loop very quickly in 10, 15 minutes, or probably even less. And as I was saying, AI may be a very good candidate to process the data on the edge. This is because it's state of the art of many applications, and also the hardware is very versatile. More or less, the hardware is the same for the different models every time you want to do an inference. The advantage is that you're going to have an autonomous system, much faster system, is also data efficient. And the idea is not to substitute, but to complement the bent pipe. So to provide both the capabilities, to store the data and to process on board. What we have seen before is edge computing, but in general, you can extend this paradigm to what we call cognitive cloud computing space. So the idea of having a distributed computing capability space where satellites can communicate each other, and you not only have Earth observation satellite as part of the paradigm, but also different other spacecraft, for instance, any kind of probes, so you can think the ISS itself and others. Of course, is this useful? We think it is, but to understand what is going to happen in 10 years is very difficult to say. That's why we are now conducting 3 parallel studies to try to create a long-term vision. But for the moment, what we think is that it might be very useful, and we see that the possible application in a second. Let me just clarify, when we talk about edge computing in space, where actually we are doing the processing. We have, so if you know satellites a bit, you know that you have 2 main elements. One is what is called the platform. The platform is what is responsible for the main satellite functions. So it's responsible to make sure your satellite can distribute the power, can distribute the clock, can acquire on the earth, so control the altitude that stays on the orbit. Is not really related to the, let's say, scientific or commercial purposes of the mission itself. So the main computing element is called onboard computing. And then you have the payload. The payload is the part of the mission where you actually, it's actually responsible for the scientific purpose of the mission itself. So when we talk about, for instance, fire detection, this is done on the payload. It's where you acquire the data, you store the data, and then you send it to her. Today, of course, even if edge computing is relevant to both, we discuss only about the payload. We are not talking about the platform. So as I was saying, for the moment, everything might look a bit abstract, but let's try to see why you might have some applications for edge and cloud computing space. So first of all, as I told you, one application might be low latency early alert systems. Nowadays, sending all the data and processing them very quickly is not really feasible, or it's very expensive. So the best way, and probably the most efficient way to do it, is using edge computing. So you pre-filter the space, you know you have an actionable information, and you send it when it's needed. This can be very valuable for any, let's say, civil security application, like disaster monitoring, early alert, disaster response, also surveillance application like maritime surveillance. You want to try to prevent drug dealing, illegal fishing. This kind of application can really benefit of this. There are also commercial use cases. Sending the data becomes expensive, or might be expensive for some application. Maybe it's not for ESA, but for companies that want to provide only actionable information to end user and not the data, sending all the data might be not really, let's say, commercially viable. So the best way, one way to do that is pre-filter the data that you need. For instance, if you consider that when you have optical imagery, more than 50% of data is covered by clouds, you can easily understand that if you detect clouds on board and then you discard the cloud covered image, you can save at least half of the bandwidth that you have. And this has been done, at least a demonstration of using AI on board to do that has been done as part of the FISAT-1 mission. It was the first mission using a commercial processor, a commercial AI processor for doing deep learning inference on board. And indeed, the use case was cloud detection. So with AI, you can create a cloud mask, count the many pixels you have over the entire acquisition that are cloud cover, and then you can decide whether to keep or not the imagery. But you also have, let's say, more commercial applications. If you move from the logic of having a single satellite, but you have a cloud, you can imagine that you can use distributed computing to have a sort of cloud in space. And cloud can be used for different applications. One is data center, not only to process the information from space itself, so to collect the data from satellite, but potentially also from the end user. It's a very controversial use case, I have to say. There's a lot of research to understand whether it really makes sense, but if you read around, there are people start speaking about it or actually implementing space-based data centers. And the cloud is not only useful to process the data, but also to synchronize acquisitions, in the sense that if you have a satellite that acquires on a certain image and it gets actionable information, for instance, there is a fire, you can task another satellite to look at that area very quickly. And this leads to novel acquisition systems. For instance, one of the most interesting paradigm that might be enabled by edge computing is actually tip and queue. So let's assume you have a satellite 1 and a satellite 2 with very different sensors. If I talk about SWOT width of a satellite, are you familiar with the terminology? Well, the SWOT is how large is the area you're looking at. For instance, the equator can be divided into a certain number of SWOT width. The bigger is the SWOT, the less number of passages you need to pass over to the same area. So you have a lower, basically, you have a lower time for which the satellite passes over the same area. So you can monitor changes more frequently. But of course, if you're going to have a very large SWOT width, the pixels that you have are divided over a larger area. So the spatial resolution that you're going to get becomes lower. And this is a problem for Earth observation when you want to have acquisition with higher resolution. So you might have a satellite that do the opposite. So basically satellites that have a very small optical, very small SWOT width, very high resolution, but then to monitor changes, we need to do a lot of passes before passing again over the same area. It's a bit of the Heisenberg principle in determination. You cannot have both at the same time. So one way is to have the satellites collaborate using this paradigm. Let's assume you have the first satellite passing over the Earth and it scouts something that might be interesting, but due to the limited spatial resolution, you are not really sure what you're looking at. So if you want to get a high spatial resolution acquisition over the certain area, you can tip the second satellite that will go over that area, and the next satellite that might also have steering capability, so it can also turn to look a bit sideways, passing over that area can do a high spatial resolution acquisition. So in this way, you can increase the resolution of the acquisition while keeping a low revisit time, so high frequent acquisition. Why edge computing is important? Again, at the moment is the best way to process information and to make the satellite coordinate very quickly. Of course, to do that, you need to have onboard computing capabilities. And it becomes very important to have hardware that is able to do that. So we are now talking about the metrics to judge the hardware, and then we will talk about the different possibility that you have to do onboard computing, hardware for onboard computing. So, of course, one of the first metrics that you think is computing performance. I think if there is anyone into gaming, you know very well why it's important. But from space application, this is very important because if you want to send, for instance, information quickly to Earth, it's very important that you provide, you're also able to process the information very quickly in space. So that's why computing performance is very important. How do you measure the computing performance? Well, there are different metrics. One is floating point. Others, there are specific benchmarks, so algorithms that you run on the hardware, and the quickest one is the best according to that algorithms. There are others. Let's try to guess what is important. Any guess? Now, if you have to buy a computer, what you're looking at? I see. Well, GPUs, but no, in terms of things that you're looking at. Are you going to buy the same computer for 10,000 euros? The cost, for instance, is one. But let's talk about cost later. One of the elements, for instance, is energy efficiency. So you might know energy efficiency a bit because the more is expensive, the more is energy consumptive, the more is expensive for you to pay home. But in space, there are also other problems. Let's say general indication, you might have others. So there are different energy or power metrics. One is that you can measure the joule if you want to measure the energy, or the energy per operation if you want to go into the hardware metric. From the application perspective, one of the metrics is the energy that you are going to do for an inference. If you do it, if you have an AI model, you want to know how much energy in joule you need to use to do one inference on the image that you have. So why it's important? Because satellites are typically have limited energy budgets. So it's not very easy to process data in space as you will do on Earth. So you also have thermal constraints. It's not only a matter of energy, but when you dissipate power, when you produce power, you need to dissipate. And very different from what people believe, dissipating heat power in space is not very easy. So there's actually a problem. If your power consumption is too high, then you need to have a very efficient way to dissipate heat. I have a question for you. Do you know what's the difference between energy and power consumption? Because it's not the same thing. Okay, well, from the physics, the energy is basically the power that you're going to dissipate over a certain time. So it's very important to be both power and energy efficient, because the power is the power that the battery itself has to provide in that instant, and also is the heat that you're going to produce in instant. The energy is what you're going to get over your entire orbit, and that's also a problem because your battery might not have sufficient energy to do a lot of computation in space. There is also another metric that you might not be very familiar with, is radiation. So computing in space is tricky also because it's not the most approachable environment. Radiation creates problem and interferes with the hardware itself. You have three main phenomena, let's say. The first one is a single level effects. So when you have hardware in space, radiation hit the hardware. The hardware might trigger the pulses that radiation creates and might lead to faults simply because the hardware interprets what they get as data, even if it's not, it's just noise, if you want. These typically are errors that can be solved by resetting your satellite, but if you're not, and your satellite ends up in a state that is not known or is not managed, maybe you lose your satellite. So it's very important that you have a system that for which your hardware can be resetted in space. You have also a more, let's say, long-term effect. It's called total ionization dose. When particles hit the hardware, they start accumulating, and after a while, they destroy your transistor. So basically, this effect is a charge accumulated, basically sets a limit to your reliability, to your life in space of your device. Then there are also more scale effects like the single level latch-up. When you have a high energy particle hitting your hardware, they might create a positive feedback loop that amplify the current in the transistor, and the transistor dies immediately. So as you can see, processing space can be dangerous, and radiation really sets a limit to your reliability. So it's important that the hardware is also radiation tolerant. Cost, as I was saying before, is important because, of course, you need to pay for the mission. Or if you want to have a commercial mission, you want to minimize your cost to maximize your profitability, no? And it can be divided mainly in two components. You have the so-called non-recurring engineering cost. So it's everything that you need to pay before selling the first device or using the first device. So here is the manpower to develop, for instance, your application and everything. And then you have the recurring engineering cost. So all the elements all the cost elements that are proportional to the number of pieces that you're going to use. There are also other parameters like the size of the mass. Why they are important? Well, the size, because if you're going to launch a CubeSat, that is a satellite with a certain standard, you cannot fit 1 kilometer devices because they are space is constrained. And the mass is also important because, as you know, the launch cost is proportional to the mass, or at least it's dependent on the mass. So you would like to minimize the mass of your devices to minimize the cost of launches, and so the overall cost. Okay, so those are the parameters. Now we are going to review some of the devices that we can use, and we are going to describe a bit based on the metrics that we have seen. So microcontrollers, those you might know what they are. So microcontrollers are simply processor with some peripherals. So you have a core, you have a RAM, you have a storage, and then you have some peripherals. Microcontroller is so-called, as you probably know, because you have at least microprocessor or processor in your computer, they have the same hardware for all the different applications. So you change the software, you change the application. You're going to program your controller, your device, your processor, you change the software, and you get a new completed application. So they are very flexible. You can use a microcontroller for everything, but at the same time, they're not optimized for anything. The hardware is the same, whatever you want to do. If you think about gaming again, it's very easy to understand why you want a very good GPUs to do gaming, because it's optimized to do computer vision. Microcontrollers or microprocessors are not. So the performance and the energy efficiency is typically very low, and the development time is also quite easy, in the sense you need just to design your software. So if you know how to program nowadays, you can program a microcontroller. Radiation tolerance is really depending on the design and technology. They are typically using CubeSat or satellite with very limited processing capabilities. Otherwise, to do AI inference, typically you will not use a microcontroller. You will try to use something else, unless you really need, because you need to minimize the energy consumption. You might have heard of FPGAs, or field programmable gate arrays. Have you heard them? No. Okay, I will tell you. So these are programmable devices in the sense of the hardware. So microcontroller, you can program the hardware. The hardware is the same, and you change the software. Here, what you're going to do, you're going to change the hardware depending on your own application. So the algorithms that you're going to develop are mapped on the hardware itself. The difference is that if you want to do 3 multiplication with a microcontroller, if you have 1 multiplier, you need to use 3 clock cycle, because you have only 1 multiplier. Here with FPGAs, you can implement 3 multipliers, so you can do everything in a single clock cycle. Of course, FPGAs can also be coupled with microcontroller to make things more complicated. This is because some algorithms are not very efficient on FPGA. So you can have what is called system on a chip FPGA, where you have both. So FPGAs are very convenient if you understand the example that I told you before, where you have 3 multipliers when you have to do massive data processing in parallel. So data flow processing. Of course, the flexibility is very limited in the sense that, okay, you can reprogram your FPGA, but you need to redesign the hardware, and you can believe me, it's way more complicated than designing a software. Especially if you use a stock FPGA, we have to do both. And you can get very high performance. They are pretty energy efficient, but the development time is typically very high. I can tell you that for my PhD, I developed an hardware accelerator for 1 network, and it took me 6 months. So it's very difficult. It's not very scalable in terms of time as a solution. The engineering cost, the non-recurrent one, can be very high. 6 months to pay an engineer. Also, the recurrent one are higher than microcontroller. You can expect they cost at least 10 times, even more. Radiation tolerance, again, depends on the way they are designing the technology. It's possible to reduce the cost, the time. Nowadays, with what is called high-level synthesis, there are some tools that take your network and they implement for you, they create the hardware for you, so you don't need to design the hardware. Of course, you lose in performance, but you can really speed up the design. So FPGAs, that's why become very interesting device. However, the design flow is still way more complicated than for a microcontroller. Another device that is very interesting is GPUs, of course. You might be aware with them because you have in your computers. GPUs are interesting because as a lower development time than FPGA, and you can still have very high performance. And also might be very interesting, and also for the training of model, you will see there are some use case for tuning your model in space directly. They're very flexible, less than a GPU, than a CPU, but way more than FPGA because the hardware is again fixed. The performance is very high, comparable even more than FPGA sometimes. The energy efficiency is typically very poor. So you probably know, if you're into gaming again, that your GPUs is going to dissipate a lot of heat. The development time is typically nowadays with tools comparable with 2 CPU, might be a bit higher if you want to go to run large GPUs. The non-recurrent engineering is quite low because of that. The recurrent engineering, you know more than me how expensive they are. So they are comparable or a bit lower than FPGAs, but still very expensive. They have a problem. Radiation tolerance is typically very bad. The reason is because if you have particles, as you know, if you are into shooting at targets, the bigger is the target, the easiest to shoot and to get. GPUs are very big, and big means they can collect more particles in space. So typically, they are not very good in terms of radiation tolerance. That's why they are not nowadays so common for the processing space. There are also some solutions, the so-called AI chips. You might be familiar with the TPUs or the visual processing unit that are basically chips that has been designed on purpose to do efficient AI processing. They have limited flexibility because you can only use for AI, you cannot use for anything else, but they are super energy efficient and very high performant. The development time is low to medium in the sense that compared to deploy to a CPU, you might need some other steps, sometimes to quantize your model, sometimes additional steps to really map the device on your hardware. But it's not that big. The engineering time is not that high. And the cost is still low average. Radiation tolerance, low average, depends on the device. But nowadays, you don't have, at least to the best of my knowledge, chips that are designed to do AI inference in space with some, you have them, but they are a spare minority. Most of the one that I use are commercial, so the radiation is not that tolerance is not that high, just because the design has been, the device has been designed for commercial purposes in Earth. They are typically used for inference on nano microsatellites, and for instance, the FISA2 FISAT-1 that I presented before to do cloud detection used one of these devices. So in Italy, we say not gold what shines, in the sense that everything that I say is very beautiful, but of course there are so many technical challenges to make this operational. As I told you before, everything makes sense if your satellite is able to communicate to another satellite. If this is not possible, then edge computing allows you to save you minutes on the latency, but not hours. So you're going to lose most of the advantages. Power constraints. I told you before, satellites are very energy constrained. It depends on the satellite, of course, but typically you don't have the same energy that you have on the ground. Radiation, just discussed. You might have mission-specific constraints. Thermal management, again, we have discussed again. But there is also another problem that you might be familiar, you might know if you're familiar with AI training. Dataset. It's very difficult to get dataset that are really representative of what is going to happen in space. We are going to see this now in detail. In particular, we are going to discuss a bit these two aspects that are probably the one that you would be more interested, or you might end up working more with if you are working with these applications. One of the problems is indeed the representativeness of the data set. So you might expect to have the so-called domain gap problem. So what is domain gap? So when, let's assume you want to train on a certain data set, the data set you train is your source domain. Then you deploy your model on the satellite, and it's going to process the data. The data that it's going to process are in a different distribution, typically called target domain. The two distributions, for different reasons we're going to see, might not be the same. One, for instance, is that the train that you have are in a different operational scenario. Your data most likely are collected during the day, you might want to use the data during the night. It's very rare, right, in satellite, but it's just an example. Of course, if your training data set only see this kind of imagery, you can expect that with the other ones will not perform well because they are completely out of the distribution or partially out of distribution. Maybe your dataset is not sufficiently comprehensive on what of all the scene where you're going to deploy your model. For instance, if you have only images of Latvia and you want to process on board also image from Sahara Desert, you might expect the data distribution to be very different because you have very different spatial features. So this is a problem that you also experience probably with the training of model on the Earth, but this is a big problem in space as well. One of the most peculiar problem that you have for space application, and when you want to deploy data on board, most of the time you start developing the AI model before the launch of the satellite. And if the sensor is new, typically this is a problem because you don't have the data of the real sensor that you're going to test with. So, for instance, this is a clear example what was done for FISA-2. FISA-2 was another mission after the FISA-1 we are describing before, made to test different app on board. What has been done to train the model was to train the data on simulated data, starting from Sentinel-2 imagery. These are the data look like on the real one, but if you're looking at, maybe on the screen you cannot really see it, but the target domain is very different. For instance, there are some vertical lines that are called stripe noise. I'm not sure you can appreciate it from here. This kind of noise was not adequately modeled before, simply because you don't know the noise distribution. So you cannot do exact modeling of the data. So when you're going to deploy on board, your model will experience again a domain gap. There is also a problem if you fix the data, and you might have sensor degradation and noise drifting. So in 2 or 3 months, if your calibration is not effective, you might experience a different noise distribution again. So last reason is that it's not very easy to do on board what you typically do on the ground. For instance, many of the applications that has been developed for edge computing, especially nowadays, some years ago, due to lack of data, where the prototyping was done on Sentinel-2 level 1C. I don't know if you're familiar with the level of processing, but the data that you have on board when you acquire are very different from the data that you're going to process today. This is because there is a long processing correction chain that removes the noise, so does the so-called radiative calibration, but also does geometric calibration, so change basically adjust the bands and then applies ortho rectification, removes correction due to the Earth rotation and others. All these processing are very computational intensive. So if you are going to test your model on Sentinel-2 level 1C, make sure you can be assured that on board you will not have the same quality of processing, because it's impossible, it's too computationally expensive. So it's difficult to reproduce what you have on board, even because the raw data, the so-called level 0, is typically not available to the community. That's why when you train something on Earth, you have a domain gap again. Also because it's very difficult to reproduce what you're going to do on board. So, for instance, for Sentinel-2, the number of raw data that you are available is very limited because it's simply not distributed as a product nowadays. There might be some strategy to mitigate that. This is a very open research problem nowadays, not only for onboard application, but let's say for different application. Nowadays, the typical approach for onboard to fix the problem is simply wait. You launch, you do what you can with the source domain, you train your model, you download the data, you create another data set, you fine-tune your model, and then you upload again. Of course, this is the easy solution and works because sooner or later you will have the data to train your model. Of course, it's not the best for those who want to operate a satellite, because waste a lot of time to provide you the data just to train your model. And If you have to pay for that, then you are not happy because you cannot deploy your model immediately, but you have to pay for the data to tune your model. There might be in-orbit domain gap adaptation. There are some research now in developing unsupervised methods to train, to fine-tune your model on board. Why unsupervised? Well, simply because if you want to do it online, while you receive the data and while you acquire it, you don't have the label for them. Otherwise, if you have to label them, you have to download and you end up in phase one. So if you really want to fine-tune on board while the data you have, this might be possible, but you need to develop a method that is unsupervised. And also, you might need to have an hardware that is able to do the back propagation. So should be able to do the training. Again, probably you need something like GPUs. There is also another potential solution, very on the research side. It's basically an hypothesis, but it's to use foundation models. Are you aware of foundation models? Yes, my colleague Lorenzo should have given you some lecture some days ago. So basically, foundation models are large models trained on a vast amount of data, and the idea is that if you train on a very large distribution, part of the distribution on board might be covered by that. This is an hypothesis. Of course, it might depend on the model, on the data that you have trained. There's a lot of research. There's also a lot of challenges. Again, deploying a large model in space is not easy in terms of power and so on. Okay, but another big problem is the so-called energy constraints. Why energy constraints are the problem? As I told you before, the satellites have limited processing capabilities, and the energy that they are able to provide depends on the orbit and the solar power and the size of the solar panel that they have and so on. So basically, again, if you need to do the same quality of level or processing level that you do on the Earth, this might be very difficult to do in space. Also, for some application, you don't want to process the data, but you want to process them very quickly, because otherwise, if you need 1 hour to do the processing, you can simply download the data. You can use the bent pipe, and this is basically not really useful. So one of the questions is, do we really need to process high-end calibrated products? In other words, can AI models keep on some of the pre-processing steps and process more the raw data? Maybe not for all applications, but for some applications. This is because if you can, you save energy, you save time, and maybe the AI model works anyway. So that's what we are trying to do, to see if the AI model can process the raw data for thermal anomaly detection, volcanic eruption, wildfire. Why did we pick this application? Because especially for the wildfire, it's very important to provide a timely response. So it's a very good application for onboard AI. But how the raw data look like? Do you have an idea? Well, to understand that, we have to start from somewhere. So we use Sentinel-2 data. Why Sentinel-2 data? Because it's the only sensor for which we managed to find the data, the raw data. It's very simple. It's not the best in the sense that you cannot do onboard AI on Sentinel-2 data, but at least it's interesting to start from somewhere, let's say. So Sentinel-2 is a multispectral sensor. Do you know what it means? Multispectral means that you have multiple channels in the visible, near, infrared, and SWIR ranges, basically. So the satellite is a push broom. Push broom means the acquisition is done while the satellite is moving. The satellite focuses an area, and then when it moves, it starts acquiring information, fusing multiple acquisition over time, basically. So the satellite basically sweeps over a certain area. The acquisition stops after 3.6 seconds. And from the level 0 perspective, every 3.6 seconds is producing a granule. A granule is simply the minimum area that the satellite produces itself in the level 0. Something that you might not know that if you only process the level 1, that the bands, so the different spectral channels are not spatially registered. What it means. So those are 3 level 0 acquisition for the bands 2, 3, and 4, so the RGB. Okay. This is the acquisition on a certain timestamp. As I told you, after 3.6 seconds, the satellite produces a new set of acquisition for each band. So basically, the satellite first acquired this, and then after 3.6 seconds, it's moved a bit and acquired this. Very simple. So this can be stacked, this can be stacked, and this can be stacked vertically. But I don't know if you noticed this, but if you look at this area, you can see this area is actually here. But this area is not here. So that means if you're going to overlap these three acquisitions, they will look like that. So spatially speaking, the bands are not registered, they don't look at the same area. And as you can imagine, this is a problem in the sense that if you're going to do an inference on the AI model, it might be not very easy to do it. Your convolutional filter will not process the same area. In addition, there's no radiometric processing in addition to the bands. So you might have noise, as I showed you before. So how do I solve the problem? Well, typically speaking, there are multiple ways. Some people have mechanical models to do the registration. They simply know, depending on where the satellite look at, the altitude of the satellite, the velocity, the speed of the satellite, they know how the different bands will be different. By using a mechanical model, they can simply do an adjustment of the band problem, band registration problem. Other approach might use computer vision. So they might extract key points over the different areas from different bands. They can use key point matching. And you can see, for instance, since this point corresponds to that point, all the bands have averagely a vertical and horizontal shift. Indeed, there is an inclination among the bands. As you can imagine, key point extraction is computational intensive, and you might not want to do it on board. So what we did as part of the research was to build a thermal hotspot dataset in raw Sentinel-2 imagery. Basically, we built the dataset with a lot of raw data acquisition, not a lot, but what we did acquisition, containing volcanic eruption and wildfires. The data that you have is typically enough to train an AI model because the data are very big and then can be spread in a lot of multiple patches. So you will not have only 146 images if you look at the number here. You can download the dataset if you want, and there is also an API that allows you to process the level 0 very easily. Because doing from scratch, you can rest assured is not that easy. So with this API, you could do it if you're interested to test it. So our idea is indeed to try to test the image from the raw data by minimizing the preprocessing step. So instead of doing the accurate band registration, as I showed you before, what we did, we calculate the average shift along track, so vertically, and across track, so horizontally, and we apply always the same shift for all the bands. Does it work? It works okay. At least is enough to do a very simple registration without needing to do key point extraction on board. So it's a lightweight processing. It's not going to be with the same quality of what you do on Earth again. Then you simply divide the image in multiple patches. This is because the image is very big and it's difficult to do the inference on a huge image on board. And for each patch, we are going to do classification, fire, not fire. So in the end, we are going to create basically a thermal anomaly map. Red, sorry for the mismatch. Red means thermal anomaly, white, not thermal anomaly. And we did the inference on what is called Myriad XPPU, is one of the AI processor hardware that I was talking before. I can show you some qualitative results. Basically, if you look at what we have some false negative, but sometimes the model, but the number of false negatives here is just one. All the rest, even if you look at the spreadsheet, you think there's no fire. If you zoom, you see that there is a bit. So of course the model here is right. So it means the model is able, in most of the cases, to detect even very small fire in the image, and so the patch is actually classified correctly in most of the cases. And in terms of energy, what is very interesting is that by using a Raspberry Pi and the AI processor that I told you before on a real space hardware, what we got is a latency for the entire image average on the data set of 1.8 seconds. That is less for every image than the time. It's basically the half of the time that you need to acquire the image. That means you are able to process it in real time. Of course, this is very interesting. You can look at the paper that is in the references to look at the qualitative results, because also quantitative, the model works quite well. The average power consumption is 5.5 watts. That is quite good to do this kind of processing. Just to show that this kind of raw data processing might be very interesting for your application. So edge computing space is attracting the interest of the research community for the application that I told you before. There are so many technical challenges now, and as you can see, the technical challenges are more than 360-degree. Hardware, AI perspective, processing perspective. So there might be a lot of different profile careers working on this topic. There's for sure need for further research to make it operational. Mostly today, there are commercial missions, but most today are technology demonstrators. That's why further research is needed. And we are very active in the Philab and also in ESA on this topic. So just to mention that in the Philab, we are very open to collaboration, and working with us is very easy. We welcome visiting professor. We welcome visiting researchers to stay with us in the Philab and to work on these, but many other topics. We welcome research. We hire research fellow to conduct research on specific topic. We co-found PhD, and of course we hire early graduate trainees as all the rest of ESA. But we also do internship. We also have national trainee. So if you are interested in this and other topic, don't hesitate to take a look at the Collaborative Innovation Network website, where you can submit your own proposal to work on a specific topic. Maybe this one, maybe all the others relevant to the Philab. You might find the work by other visiting researchers, or you can also follow us on LinkedIn to see the work that has been done, the new people that has come to us, and so on. If you want to know more about the Philab, do not miss the spotlight session and big data from space on the day show, October 2nd at 5:50 p.m.